14.4, the merge sort algorithm. So this is another kind of algorithm. This is a very popular kind, and it's significantly faster than selection sort. And what this does is it has a basic idea that if I have two arrays that are already sorted, it's very easy to put them together. For instance, page 639, if I had the following arrays, 5, 9, 10, 12, and 17, followed by 1, 8, 11, 20, and 32, I could put those two and combine it into one larger array. And all I'll do is the very first time through, I look at the very first two elements. So I check here, and I figure out which one's smaller. So my 1's the smallest, so that goes in the beginning. 1's no longer an option. All right, so now I check 5 and 8. 5 is the next one, so I put the 5 in there. That one's gone. Now I check 8 and 9. Between those two, the 8 is the smaller one, so that one's gone. Now I check 11 and 9. That would be 9. Now 9's gone. Now I check 10 and 11. Now, so far we've been alternating lines, but here I've got two in a row. The 10 is also smaller, so that one gets knocked out. I check 11 again versus my 12, and the 11 goes there. Now that one's out. Now I'm going to check 12 versus 20. All right, 12 is smaller, so 12 goes there and knock that out. Now I'm checking 17 versus 20. 17 is still smaller, and then I have 20 and 32 left over. So it's very quick. Obviously the problem is that the first two arrays, this one and this one, they have to be sorted before I can do anything. All right, so before I can merge the two arrays, I have to sort them. So what we'll do is we'll recursively sort them by cutting the original array in half, recursively sorting each half, and then merging those sorted pieces. And your base case is going to be obviously an array of size 1. If I had the array 1 and 8, if I split that in half, and I then have the array, I have one array called of 8 and one array of 1. Those are already sorted. So then I can merge those two together, and then I'm good. Right? If I had 1, 7, 3, 5, right? So I cut my array in half. Then I have two arrays. I have 1 and 7, and then I have 3 and 5. And then I'll cut that in half, and so I'll have 1 and 7, and then 3 and 5. I'll merge them. These are ordered, so I'll merge them, get them in the right order. I'll get these two in the right order, and then when I get here, I can just merge these the same way we did it over here. So it's pretty easy. I just have to break everything down to an array of 1, and then start sort of merging it back together. So the code for that is in your Dropbox folder and also on page 640. So I've got the parameter of an integer array, and I have the method called sort. Sort makes two new arrays. If this cuts them in half. All right, I copy them. I make a new merge sorter with my two smaller pieces. I sort the first one, I select the second one, and then I merge them together. Okay, and then merge, obviously, I just keep chopping myself up. So that is my recursive call. Keep making more and more and more of them. And this is actually a pretty efficient algorithm. We're going to segue into section 14.5, analyzing it. Okay, if we were to set up the data table versus merge sort versus selection sort, you notice you get the table in page 643, where we knew selection sort, sort of a quadratic, but if I look at merge sort, 10,000 item array still took the exact same time. A 40,000 element array took 9,192, and a 60,000 element array took 19,299. But if I compare that to merge sort, 40, 170, 205. So it doesn't scale nearly the same way. Okay, so if I plot, in this case, selection sort, quadratic, versus merge sort, it's almost negligible. Okay, so you get t of n over 2 plus t of n over 2 plus 5n. So that is each for my original array. I split it in half, and then I have 5 steps left. Okay, so that would come up to be n of 2m. Okay, finish, we're not going to write down all the steps, but you all the way get all the way down to the following. N plus 5 n log base 2 of n when I get done profiling everything. Again, we're not going to worry about really so much about the coefficients, and we're going to even drop the base because they're all logarithms are rated by a constant factor. So we're going to simplify all of this down to, now I do have an n in the front here. Don't worry about the constant or that one. I've got an n, drop the base, and another n. So I have my big O notation is O n log of n, essentially logarithmic. Now this is obviously different from an O just log of n1, but again, drop your the smallest term, drop any coefficients, and what you're left with, simplified down, is going to be your big O notation. So this is a logarithmic scale, much, much slower than a quadratic. For instance, if we were going to do the difference between 100 and 10,000 elements, we get a factor of 150 times longer. So much, much more efficient than using a selection sort, although selection sort is obviously easier to write. Now, one thing, if you're ever writing an array, unless you're specifically told to write merge sort, write selection sort, you obviously need to be able to read, understand, and profile them. More importantly than profile them, know where we get those profiles from. But the arrays class has the ability to already sort. It's already written into the Java code. So if I had an integer, some integer array of initialized to whatever, I could sort A, and that's already built into Java. Okay, that is a quick sort algorithm. Don't worry about it too much, but another pretty good one. But most importantly, it's already written for you, so you just get to use it. Every time you need to sort something, you don't have to come up with it. We're obviously just showing the basics so you get an idea of how it all works and where it all has come from.